Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is More About the Gradient. As always, please be an active learner as you watch these videos. Maximizing the directional derivative. Suppose we have a function f of 2 or 3 variables, and we consider all possible directional derivatives of f at a given point. Now these gives rates of change of f of x in all possible directions. So then we can ask the questions, in which of these directions does f change fastest? And what is the maximum rate of change? The answers to these questions are provided by the following theorem. So suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative, the derivative in the direction of u, f of x, is the absolute value of the gradient of f of x. And it occurs when u has the same direction as the gradient of the vector, the gradient of f of x. So we know the path to take to get the biggest value. Let's look at the proof, and the proof is actually quite easy. Because you see, we know that the directional derivative in the direction of u, a unit vector, defining the direction of f, is the gradient of f dotted with that vector u that's down here. And we know that the dot product from way back in the beginning of this course is the magnitude of the gradient of f times the magnitude of u times the cosine of theta, where cosine of theta is the angle in between these two vectors. So we're looking to maximize this. Now the magnitude of the unit vector is going to be 1, and so this is the same thing as the magnitude of the gradient of f times cosine of theta, and that's the absolute, it's the magnitude of that vector, times the cosine of theta. So theta is the angle between the two, and the maximum value that cosine can take on is 1, and that happens when theta is equal to 0. Therefore, the maximum value of this is, in fact, this number right here, this function right here, and it occurs when theta equals 0. That is, when u has the same direction as magnitude of f. Now, before we do a numerical example, let's talk about, well, when do you use this? And you certainly can use this in optimization, but there are other physical examples that we'll talk about here. So remember that the directional derivative of a function can be calculated in any direction, but the gradient vector gives additional information about the derivative, including directions of interest. For example, the area of steepest ascent or most rapid descent. So an example would be found on a mountain slope. A mountain climber must consider many different paths up a mountain. The gradient vector indicates the direction of greatest increase in the elevation of the mountain. And if you're wanting to have an easier climb, you may want to do this on a face where the gradient is less. Captains of shipping vessels must consider safe paths of travel relative to poor weather. To exit a storm, the ship can be steered in the direction of greatest increase in barometric pressure. And paramedics at a ski mountain must find the path of steepest safe descent to bring a patient to the hospital as quickly as possible. The direction of steepest descent is given by the opposite of the gradient vector at the given point on the mountain, and that's because of the definition of absolute value. And so they can determine that and use the steepest of those that is safe. Okay, let's apply this then to this problem. So if f of x is y is equal to x e to the y, find the rate of change of f at a given point, and the point is x is 2 and y is 0, and this is in the direction of going from P to Q. So this is the vector. We're going from this point to this point, and that is the vector that we're looking at. And then part B is, in what directions does f have the maximum rate of change? You're finding the rate of change along this specific vector, but what's the maximum rate of change? What is that direction? What is that unit vector? And what is this maximum rate of change? You know what to do. Let's see how you did. Okay, well, so what we can do to find the rate of change at that point is we can compute the gradient of f of xy, and that's going to be the vector pointing bracket fx, fy, where these are the first partial derivatives with respect to x and y, and I do the calculations and I get that. And then I evaluate the gradient at those points, and I get that this is 1, 2. Now the unit vector in the direction of PQ, now I have to figure that out. I go from here to here. It's going to be pointing bracket minus 3 halves 2 into pointing bracket, and then I normalize this, so I make this into a unit vector, and that calculation is u is equal to minus 3 over 5 comma 4 over 5. And again, you want to check this calculation for yourself. So the rate of change then is the dot product of the two, so it's the dot product of the gradient, evaluate at that point, times, and not times, but dot product with this unit vector. I do the calculation, I get 1. And so that tells us that the rate of change in that direction at that point is 1. Now, it moves the fastest in the direction of the gradient, and so this, the gradient at 2, 1 is 1, 2, so the maximum rate of change is the absolute value of, or the magnitude of the gradient evaluated there. That's the magnitude of the vector pointing bracket 1, 2. And if you do that calculation, that is the square root of 5. So you see this direction is not as big as this, because this the square root of 5 is 2 point something, and this one is 1. And one of the things you notice graphically is that if we plot the level curve, the gradient appears to be perpendicular to this, and that makes sense because if I were to go along a path Q, I'm not going up as fast here. You can tell just by the level curves that I'm going up much faster. So it makes sense that it's steep. And here's a three-dimensional graph. Here's the surface, and there is the vector that we're moving along. We can also use this technology or idea talking about tangent planes to level surfaces. So suppose that S is a surface with the equation f of xyz equal k. Now this is a conceptual kind of thing, but the level surface of this function of 3 variables, we have that, and we let p x0, y0, z0 be a point on S. Then any curve that lies on the surface and passes through P it's a continuous, assuming that I have continuous first derivatives, and that's a vector function r of t and x of t, y of t, z of t. And t0 is the parameter that corresponds to that specific point that I was talking about, this point P. Since C lies on that curve, it must satisfy the equation. That's just this one. And if we take derivatives of that and we use the chain rule, we find that this is the partial of f with respect to x times dx dt, partial with respect to y dy dt, partial with respect to z dt is equal to 0. But that is the same thing as the dot product of the gradient with the derivative of the vector function equaling 0. So that means that the gradient vector at P is perpendicular to the tangent vector, which is, we know to be r prime at t0, to any curve that passes through P. That's basically proving the perpendicular thing that we observed before. So if the gradient does not equal to 0, it's natural to define the tangent plane to a level surface as the plane that passes through P and has a normal vector that is the gradient. And so if we use the standard equation of a plane, here's a picture of what we're really talking about here. We get this, and again, these are the coefficients. We knew this from the previous chapter. So this is x minus x naught, y minus y naught, z minus z naught, and the coefficients are the partial derivative evaluated at that point is equal to 0. And since we have this, we also know that the normal line, that these are the direction vectors, and so the normal line to that surface at P is a line passing through P and perpendicular to the tangent plane. So the direction of the normal line is given by the gradient vector evaluated at x naught, y naught, z naught, and that means that the symmetric equations are x minus x naught equal over the derivative evaluated at that point, y minus y naught over that, and z minus z naught divided by that. And so we can look at a special case in which the surface S is of the form z equal f of xy. That is, S is the graph of a function f of two variables. Then when you rewrite this equation this way, you have that f of xyz is equal to f of xy minus z equals 0. See, we're making that equal to 0 like we had it up here. So then when regard S as a level surface with k equals 0, then we find that these are the values that we get. Now this is an important special case, and we'll in fact use this when we're computing integrals later. So the partial with respect to x is going to be the partial with respect to x of lowercase f, and this is of the partial of lowercase y, and this one is minus 1. And again, this is a result we're going to use later. And so you can get this, which is equivalent to the equation that we found before for the equation of a plane. So let's apply that then to an example. Find the equations of the tangent plane and normal line. There are two questions here at this given point. And this is minus 2, 1, minus 3, and this is the ellipsoid that we're looking at. And you see we've got that equal to 3, so we're going to move that over to the other side to look at that. You know what to do. Let's see how you did. Okay, so this is what f of xyz is equal to, so we'll take the partials and evaluate them at that point. And so what we're going to get is this is the partial with respect to x, this is the partial with respect to y, and this is the partial with respect to z. And then we evaluate it at that point, and we get these values. And so we can use our equation for the tangent plane at this point. Then it's going to be minus 1 times x minus a minus 2 is going to be 2 times y minus 1. And this was a minus 2/3. You couldn't see it. I cut it off. But that is minus 2/3, and this is z minus a minus 3 equals 0. And you can simplify that to this expression. Now, by the equation that we found for the symmetric line, then these are the direction coefficients that are in the denominator, and then the top it's x minus x naught, y minus y naught, and z minus z naught. So those are the equations of the tangent plane and the tangent and the normal line. And here's a picture of that showing, here's our ellipsoid, and there is the tangent plane, and you can see that that seems to line up with what we wanted. So we're finding that the gradient vector then is very significant. So let's summarize the ways that that is true. So a function of 3 variables and a point in its domain, and we're going to consider that first. On one hand, we know that this gradient evaluated at that point gives the direction of fastest increase. On the other hand, we know that this gradient is also orthogonal, perpendicular to the level surface. And these two properties are quite compatible because intuitively, as we move away from P on a level surface, the value doesn't change at all. So if we went perpendicular, you should get maximum change. And in fact, we actually proved that. In a like manner, we consider a function of two variables and a point P in its domain. Again, the gradient gives the direction of fastest increase, and it also can be shown, and I think we actually did show it, that the gradient is perpendicular to this level curve that passes through P, and there's kind of a picture showing that as the level curve. And so if we were considering a topographical map of a hill showing elevations, and f of xy was the height above sea level at a point, then the curve of steepest descent could be drawn by being at a point. I move in the direction that is perpendicular to the curve at that point. But then I will move at a direction that's perpendicular at this point. Again, I'm jumping from level curve to level curve, perpendicular at this point, and so on and so forth. So you see my steepest ascent would be along this, where at each level curve where I have a change, I recalculate my direction. Computer algebra systems have commands, many of them do anyway, not all of them, that plot sample gradient vectors. Each gradient vector is plotted at some point, and you can see here's an example of such a curve. This curve was z equals f of xy. This is the level curve for that, and this is x squared minus y squared, which means these are hyperbolas of various kinds, and that's a contour map of this for various constants. And the gradient vectors, you can see that they are perpendicular at every point to this. And in your differential equations, you'll talk about finding orthogonal trajectories that is very closely related to this. And here's a simpler example perhaps of that. Here's an ellipse, and I just take one of the level curves, but then I can plot the gradient vectors at these various points. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all. More later.